Hello. Hope you all are all doing well and had a good weekend. Monday again. Okay. So we have gotten not ahead of ourselves, but a little ahead of ourselves as far as naming and stuff is going. So we can sort of casually go through the rest of naming. We don't have to like stress about getting through it, which is nice. We did everything in as far as ionic stuff. So remember, ionic means that there's ions. So there's positive and negative charged particles, atoms or polyatomics that are sticking together. And we did it with regular and varying charges. So let's do a little bit of practice with that before we move on to molecular. So I want you to name each of these things. CaNO32 and FePO4. I'll give you 3 minutes. All right, so this first one here is a metal combined with a polyatomic ion. The metal in this case has a predictable charge, so we don't need any sort of Roman numeral. So I list the metal first, calcium. I don't need a Roman numeral. And that second thing is nitrate, which is a polyatomic ion. So I just write the name nitrate. I don't change it. I don't ATE it. I don't ITE it. I don't do anything like that. Just keep it straight as. The second one here is a metal with a polyatomic ion as well. The polyatomic ion will not always be in parentheses, right? This one's in parentheses because it's got a factor of 2, or there's 2 of them. If you have more than one, it'll have parentheses. If you only have one, you've got to sort of find the polyatomic ion. So in this case, we have iron. Iron has an unpredictable charge, so I do need a Roman numeral. And then this thing here is known as phosphate. So it's important to know the charges on your polyatomic ions because they're just as important as how many atoms you have. So phosphate has a 3- charge, which if this whole thing has to equal 0, I know that this then needs to be a 3+. So this should be iron 3 phosphate. Any questions on that, on those two? Throw it in the comments or just pull your mute off. Okay, got some more practice with these. So name these guys here. I'll give you 106. I'll give you 3-4 minutes for those. Okay, so with these here, similar thing to what we did before, we've got a metal with a polyatomic ion. So this is magnesium. Magnesium has a predictable charge. It's in column 2, so we don't need to put any sort of Roman numeral. And that second thing is sulfite. This second one here is magnesium as well. So we don't need a charge. In Roman numerals, we do need to name the polyatomic, which is sulfate. Remember, the ites are 1 oxygen less than the eights. This one here, we've got Pb3PO42. Okay, so this is lead. This is PO3 actually, so this would be phosphite. We need the Roman numeral here. This is phosphite. Phosphite has a charge of 3 minus. All right, so if we have a charge of 3 minus and I have 2 of them, that's an overall 6 minus charge. So this has to be a 6 plus charge, but there's 3 of them. So we divide the 6 amongst 3 leads, which would give us a lead 2 phosphite. Any questions on those? And where I got those numbers from, where the charges are coming from, so on and so on. All experts, all naming experts. Okay. Okay, just for fun, here's some more. So go ahead and name these. I think that's it as far as the naming is concerned in that direction. We've got Fe2SO43, Ba3PO32, NiCO3. All right, so first one here, we've got iron with an unpredictable charge. Well, iron always has an unpredictable charge. So iron, we need a Roman numeral, and this thing is sulfate. When looking at what our charges are, sulfate is always a 2-, and there's 3 of them, so 6-. So this needs to be a 6+ distributed over 2 iron. So we divide it by 2, which will give us iron 3 sulfate. This next one here, metal and metal and a polyatomic ion, that thing's barium. Always has a predictable charge of 2+, so we don't need to say it. And then this thing is phosphite. It's got the 3 instead of the 4. This thing here, nickel and carbonate. So nickel, carbonate. Nickel has an unpredictable charge, so we got to figure it out. Carbonate is always 2-, and there's 1 of them, so this has to be 2+. So nickel 2 carbonate. Hopefully that's clear. All right, so we're going to move on to, we spent most of the first part of this chapter talking about ionic stuff. So we're going to move on to molecular compounds. And in a molecular compound, this is where we have 2 nonmetals. And they are going to have what's known as a covalent bond. And a covalent bond is where they're going to share electrons to achieve a stable electron arrangement. You'll learn how to name these things, some basic ideas of why they bond the way they do. So molecular compounds form when atoms of 2 or more nonmetals go ahead and share electrons to create a covalent bond. Valence electrons, and when we say valence electrons, we just mean the outer electrons, are shared by the nonmetals to create an octet or a duet, some sort of stable configuration. So we can talk about hydrogen, the hydrogen molecule, H2. So this is known as a diatomic molecule. So there are certain elements out there that when they're by themselves, they would rather partner with a buddy than to exist as a sole atom. So hydrogen is one of those. Hydrogen would rather pair with another hydrogen than it would just existing as hydrogen on its own. Why is that the case? Because when we have 2 hydrogens next to each other, it gives them the electron configuration. It allows them to share electrons in a configuration that is arranged like helium. So they become stable within their electron configuration. So here's a picture. So this hydrogen over here has 1 valence electron. How do we know it has 1 valence electron? Because it's in column 1. So remember the column that you're in for the main groups, that's how many valence electrons you have. So if you're in column 7, for instance, where fluorine, chlorine, bromine, iodine are, those all have 7 valence electrons. If you're in column 8 minus helium, you have 8 valence electrons. So this guy has 1 electron, this guy has 1 electron. They're not going to transfer electrons like they would ionically, because if this hydrogen was to move this electron over here, this would not have a stable configuration. It would have no electrons and have an electron configuration, which isn't stable. This thing would be stable. So instead, what these 2 hydrogens are going to do is they're going to share these 2 electrons. So they're going to move closer together. The attraction is going to pull them closer together. And then they're going to simultaneously share these 2 electrons, or we can see there's this sort of overlapping happening. And now this hydrogen has partial access to 2 electrons, and this hydrogen has access to 2 electrons. So they both have a stable electron configuration. So a stable electron configuration is going to be 8 electrons, unless you're super teeny tiny like hydrogen, helium, and lithium. Those guys will be stable with just 2 electrons. So fluorine does the same thing because the diatomics are, we'll talk about it in a second, but fluorine is another diatomic. So over here, this fluorine all the fluorines are in column 7, so they have 7 valence electrons. So this is so close to an octet, or it's so close to having 8 outer electrons. This fluorine over here also has 7. So what they do is they just move closer together and they share those 2 guys that are not paired with anybody. And so now what we have is fluorine over here. We have this fluorine with access to 8 valence electrons and this fluorine with access to 8 valence electrons. So now they're both relatively stable in their electron configuration. The electrons that aren't involved in bonding are known as lone pair electrons. The electrons that are involved in bonding are known as a bonding pair. And sometimes instead of putting them as 2 dots like this, they'll draw it as a line. And the line means that there are 2 electrons there. So fluorine is another thing that likes to form a diatomic. Now, for people who've taken 092 and another chemistry where you guys did Lewis dot structures, this is like the extent of Lewis dot structures. We're not going to go into it very deeply, okay? And we're not going to do the 3-dimensional shapes as well. So you don't have to worry about like tetrahedral, trigonal planar, all that sort of stuff. We're not going to have time for that. But do know which ones are the diatomics: hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. So it makes sort of an upside down L, including hydrogen. So you might want to highlight those on your periodic chart. One way, have no fear of ice cold beer, but cold is talking about chlorine, not carbon, and beer is talking about bromine, not boron. So everything else on the periodic chart exists atomically or as sole element atoms. They don't molecularly bond like this. These are the only things that are diatomics. So it's important to note this, because if I was to write a chemical formula and say, hey, sodium combines with chlorine, you would want to make sure that chlorine is written as Cl2, because if it's in elemental form, it's going to be in the molecular or the diatomic. All right, so yeah, we share bonds, okay, drawing electron dot formulas. You may see this a little bit in your homework, and we're not going to go into it a whole bunch, but let's say I've got carbon and hydrogen. Hydrogen has 1 electron to offer, carbon has 4 electrons, so we would need 4 of these hydrogens to balance it out. It would look something like this, where we've got a total of 8 electrons. Carbon has access to 8, and then the hydrogens all have access to 2. The hydrogens are happy with 2. It's called a duet. This thing here is called methane. And we're not going to do a whole bunch with dot structures. Are there exceptions to the octet rules? Obviously, there's always exceptions. So there are certain things that are happier with more than 8. Sulfur, for instance, can have up to 12 electrons. Double bonds occur when atoms share 2 pairs of electrons. Triple bonds occur when atoms share 3 pairs of electrons. Again, we're not going to spend a whole lot of time with this electron dot formula. Really don't even think that you guys get tested on this for your final. You know what, we'll go over one and I will check and make sure. I don't think that this is on your final. If it is, I will tell you, but we'll do one. So we'll do CO2. I'll do 2. Okay. For you guys, since we're ahead. We'll go over it anyway, because you may have some questions on it from the homework. So if we're going to do one of these dot structures, let's say we're going to do it for CO2. What we want to do, the first thing that we want to do is count up the number of valence electrons in total that we have. So carbon is in column 4. So carbon provides us 4 valence electrons. Oxygen is in column 6, so it provides 6 valence electrons, and there's 2 of them. So we actually want to, multiply this by 2. So in this case, we have a total of 12, 16 valence electrons to play around with. So the number of valence electrons you calculate is the number of valence electrons you have to use. You can't add electrons, you can't subtract electrons. So then I want to draw a structure that's relatively symmetrical. So like carbon is going to go in the center, and carbon tends to like to be in the center. The 2 oxygens are going to go on the sides like this. Now I have to stick them together because they're molecularly bonded. So I'm going to put a bond here and a bond here. Each of these bonds, remember, is 2 electrons. So we've got 1, 2, 3, 4. So I've used 4 electrons. So first you count up the valence electrons, draw a skeletal structure that's symmetrical, and then stick them together. Now I've got to find a home for the rest of these 12 electrons. Always, always, always fill the outer guys first, and then work to fill the inner one. Don't start from the inside out, start from the outside in, okay? So if this oxygen here right now has access to only 2 electrons. He wants to have access to a total of 8 electrons. So I'm going to add 6 more electrons. 1, 2, 3, 4, 5, 6, 7, 8. I'm also going to add electrons over here to make this guy happy. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, so now I have 16 electrons on the board. Don't ever make double or triple bonds until every electron is on the board. So at this point, when I'm looking at this structure, the oxygens on the outside are happy. The carbon on the inside only has access to 1, 2, 3, 4 electrons. So we need to make carbon also happy with 8 electrons. I cannot do this. Why? Because I only am allowed to have 16 electrons. So we want to instead share electrons. This guy has some electrons he can share, and this guy has electrons he can share. So what we'll do is we'll take 2 electrons from there, and we'll make a double bond. And then we'll take 2 electrons from here, and we'll also make a double bond. Then you want to go and check and make sure everybody's happy. So oxygen here has access to 2, 4, 6, 8. Oxygen here has access to 2, 4, 6, 8, and carbon in the center has access to 2, 4, 6, and 8. So this would be the correct dot structure. Let's do NH3. So in the situation with NH3, nitrogen is in column 5 of our main group, so it gives us 5 valence electrons. Hydrogen is in column 1, so it gives us 1 valence electron, and we have a total of 3, right? So I've got to multiply it by that. So in this case, I get to play around with 8 electrons. Now, in order to make this symmetrical, I need to put nitrogen in the center. So we'll put nitrogen here. 3 hydrogens on the outside. All right, then I need to stick them together. Stick, stick, stick with a bond. At the current moment, all the hydrogens are happy, right? This hydrogen has access to 2, this hydrogen has access to 2, and this hydrogen has access to 2. Remember, hydrogens like 2, okay? Hydrogen likes 2. Everything else likes 8. So the number of electrons I have on the board, 2, 4, 6. I need to have 8 electrons on the board, so I have to put 2 electrons somewhere. I can't put them on any of the hydrogens. Those are already happy, so I'm going to put them on the nitrogen. Now there are 8 electrons on the board, and everybody is satisfied. The hydrogens all have access to 2, and this nitrogen has access to 8. We'll do one more. Let's do, CCl4. So in this one, first we add up how many valence electrons we have. Carbon is in column 4, so it provides 4. Chlorine is in column 7, so it provides 7 valence electrons, and we have to multiply it by the fact that we have 4 of them. So 7 times 4 is 28, plus the 4 gives us 32. So 32 electrons to mess around with. That's how many need to be on the board. When looking at this structure, carbon always goes in the center, and the only way I can make something symmetrical is if I put carbon in the center. So carbon in the center, and then I'm going to put my chlorines around it. We need to stick them together because they are bonded. So I'm going to put a bond, 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 and bond. Now make the outer guys happy first and then work to the inner. So we can start with this chlorine over here. This chlorine has access to 2 electrons. It wants 8, so I'm going to add 6 more. Same thing with this chlorine, we're going to add 6 more. Same thing with this chlorine and this chlorine. And if you're wondering, will the instructor like really count all those dots? If this is on the test, yes, we do count all the dots. I don't think it is. I have to double check. So count up and make sure we've got the electrons right. There are in fact 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 26, 28, 30, 32. So we have 32 electrons on the board. This chlorine has access to 8 electrons, so it's happy. This chlorine has access to 8 electrons, it's happy. This one, happy, happy. And then the carbon in the center has access to 2, 4, 6, and 8. That's also happy. So the structure is done. So that's what all those bars and dots mean when we're looking at molecular compounds. So when we're naming molecular formulas, this is kind of the more important part. We follow a totally different system than the ionic. So everything that you used for ionic, balancing charges, Roman numerals, don't use any of that here. When we're naming a covalent compound, the first thing is to identify that it is covalent or molecular. So it's 2 nonmetals. Then what you want to do is you write the first nonmetal in the formula, and you say the full name. The second nonmetal is named by using the first syllable of its name followed by IDE. So we do IDE. If a subscript is used in the formula, we have to add a prefix to specify how many we have of each atom. So whereas with the metal nonmetal, you didn't have to say you have 2 of the metals and 3 of the nonmetals. In this situation, we do have to tell you. So we don't worry about charges, but we do worry about subscripts. When we have vowels of O and O or A and O, we can omit one of them. This way is, I think, much, much easier than the other way. So here are all the prefixes. 1 is mono, 2 is di, 3 is tri, 4 is tetra, 5 penta, like a pentagram, 6 hexa, hexagram, 7 hepta, 8 octa, 9 nona, and 10 deca. You do need to know 1 through 10. So you pretty much just smush these things in front of the elements. Now, what element comes first? The thing that's more metal-like. So if I'm combining something like sulfur and oxygen, I would list sulfur first because it's closer to the zigzag line. If I was going between phosphorus and chlorine, I would list phosphorus first because it's closer to the zigzag line. So the more metal-like thing. So let's try one of these over here. C2S5. C2S5. So the first thing is to identify that it is in fact molecular and that that you can use this system. So this is molecular. We've got 2 nonmetals. I am going to say the name of the first thing, and I have to specify how many of them I have. So in this case, I have 2 carbons, right? So I'm going to call this dicarbon. And then I tell the reader how many of the second thing I have. So the sulfur, I have 5. So it's going to be pentasulfide. We do IDE the second thing. Dicarbon pentasulfide. I hate using the annotation thing here. So I'm going to go over to our whiteboard and we'll do a couple of these. So mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca. Okay. So there is one exception that you need to know for this. And that's if you have 1 on the first, you can drop it. So I'm going to write this thing here. C. Oh. Following our system, we would call this we would call this monocarbon, 1 carbon, monoxide, 1 oxygen. But mono, only on the first thing, can get dropped. Okay. So we don't call this monocarbon monoxide, we call it carbon monoxide. Mono is not allowed to be dropped on the second, and you can't drop any other prefix besides mono on the first. So if I wrote this, C2O, I would not call this carbon monoxide. I would have to call this dicarbon monoxide, because we don't drop anything greater than the mono. We don't reduce. So if I had C2O2, I would not call this carbon monoxide because the 2 and the 2 reduce. I would call this dicarbon dioxide. So hopefully that kind of clears up all of the exceptions. Really, there's only the one exception, this thing right here. So let's do a couple of these. Well, I will give you a couple and I want you to tell me the name. P4Cl2, SiBr6, C3F9. If you didn't have the prefixes written down, you can just look up on your phone or your computer real quick, molecular naming prefixes or naming prefixes, chemistry naming prefixes, and they'll pop up for you. There's nothing like looking out the window and seeing your husband like tearing the porch up. I have no idea what he's doing. He's supposed to be working right now. Like he has like a legit job. He's an architect. He's not, he does not do construction, but he's like literally has a crowbar. My guess is that there's some animal underneath the porch and he loves animals and he's like trying to rescue it. We'll fill you guys in next time on what happened there. Okay. So naming these. All right, we've got phosphorus and chlorine. I've got 4 phosphorus. The prefix for 4 is tetra. So tetra phosphorus. We don't do anything with the name. I'm on the first guy. The second thing, we've got 2 of them, dichloride, and we do IDE, the second guy. Tetra phosphorus dichloride. I feel like these make you sound really smart when you can name these. Okay, we've got SiBr6. So 1 silicon, but remember on the first thing, if we have 1, we can drop the mono. So we're just going to call this silicon, and that's bromine, and there's 6 of them. So hexabromide. No flip-flopping charges. Don't have to deal with any of that mess. You just tell me how many there are. Here I've got 3 carbons, so tricarbon. I have 9 fluorines, so nona, fluor, and I eyed it. You guys good with those? Those are easy. It's like easy compared to what the other ones. Let's do a couple going in the other direction. So I'll give you the name, and I want you to tell me what the formula is. So for the silicon, there is no mono. There is no mono if you have 1 on the first. That's the only time you can drop. So if we go back up to here, when looking at this, we don't call this monocarbon monoxide. We just call it carbon monoxide. So the mono gets dropped on the first, but we don't drop any other prefix. We wouldn't drop a di on the first. So we would call this dicarbon monoxide. Okay, that makes sense? Okay, great. So let's say we've got trisilicon heptoxide. Disulfur dichloride. Tetra bromine octafluoride. All right, you guys a minute for that. All right, so for the first one, again, we don't have to worry about flip-flopping or doing anything like that. We just look at what it tells us. Try silicon. Okay, so I have silicon and I better have 3 of them. Heptaoxide means I have oxygen and hepta is 7, not 6. 6 is hexa. Disulfur dichloride, that's a 2 and a 2. So we have sulfur with a 2 and chlorine with the 2. And we're done. Tetrabromine octafluoride. Okay, we have bromine and we'll have 4 of them. And fluorine, F will have 8 of them. And again, we don't reduce those down. We keep them as is. Why do we need prefixes with 2 nonmetals and we don't need prefixes with metals? The reason we need prefixes with nonmetals is because there's a bunch of different combinations that these things can come together as. Like we saw, for instance, CO versus CO2. It's not enough to just say carbon and oxygen. You have to tell me how many carbons and how many oxygens, because in this one, we can have 1 carbon and 1 oxygen. In this one, we can have 1 carbon and 2 oxygens. There's a lot of different possibilities, so prefixes are necessary. Versus something like this, if I say aluminum oxide, I don't use prefixes and I don't need prefixes because aluminum has a 3+ charge, oxygen has a 2-. When I flip-flop, I'll get Al2O3. That's the only combination that those 2 things are going to come together as, all right, with the flip-flop charges. Any questions thus far on prefixes? Okay. So here's some, again, some of these are the regular nomenclature names. They can also have like common names. So like N2O, dinitrogen oxide is sometimes called nitrous oxide or called laughing gas. You don't need to know the common names. You just need to know the systematic naming. So name the nonmetal, put a prefix, I'd the second guy, put a prefix. So NCl3 would be nitrogen trichloride. All right, go through here and for these here, just name those. Which one do you think? Okay, so first one here, we've got silicon trichloride, or I'm sorry, silicon tetrachloride. So we'll go with number 3. We don't want to flip-flop anything, so we don't put the 4 to the silicon like they did in 2, and we don't just say the names of them without prefixes. This one here, diphosphorus pentaoxide. They give you an option of number 2 where they drop the di. You can't drop di, tri, tetra, or anything on the first one, only the mono. This one here, we've got dichloride rather, heptaoxide 1. So if we can go ahead and just nail it in the coffin, go through and name these here. Okay, so first one here, you've seen this before, carbon monoxide. Next one, nitrogen dioxide, phosphorus trifluoride, and carbon tetrachloride. So none of them have a prefix on the first thing. So yeah, we've already gone over this. So here's a flow chart that sort of compiles everything. All right, so if you have it, if it's ionic, if it's molecular, the paths you take. So if it's ionic, are you dealing with a metal or ammonium? Are you dealing with two nonmetals, or rather metal and a nonmetal? Are you dealing with a metal with a positive or one positive ion or multiple positive ions using Roman numerals? If there is a polyatomic ion, what do you do? And then if it's two nonmetals. So here's a jumble of them together. So I want you to write the correct name of each of these. It's using like all the rules. So everything's mushed together. So first thing you want to do is identify what in fact each of them are. Is it ionic, molecular, type 1, type 2? Are there polyatomic, so on and so on. And then go ahead and name them. I'll give you 5 minutes. A minute for each one, and then we'll go over it. So for this first one, it does kind of look like a polyatomic ion, but it's not a polyatomic ion. Why? Because there's no charge in the upper right-hand corner. So if it doesn't have the charge, it can't be a polyatomic ion. So instead, this is 2 nonmetals. So I would call this sulfur trioxide. I don't include the mono in the beginning. The second one here is a metal and a nonmetal. The metal has a predictable charge, so I can just call this barium chloride. And if you're saying, well, but you have 2 chlorines, don't we need to dye it? No, we don't use prefixes if there's a metal. This thing is a polyatomic ion, and this is also a polyatomic ion. So I just say the 2 names together, ammonium phosphide, phosphite, ITE. This here is a metal with a polyatomic ion, copper. Copper has an unpredictable charge, so we need a Roman numeral, and that thing is carbonate. So let's figure out what the copper's charge is. Carbonate is always a 2- charge, so this needs to be a 2+ charge, and there's 2 of them to distribute it over. So it's copper 1 carbonate. This last thing down here is molecular. It's 2 nonmetals. So I'm going to call this dinitrogen tetroxide. Any questions on those? So I think that the naming stuff sometimes it can get a little confusing when they're all jumbled together. It's like remembering what system do I use where. So it may be useful to print out a nomenclature flowchart or have this flowchart here accessible just so that you can like sort of keep everything in order. Okay. I'm gonna get into electronegativity. No, I don't want to get into that today. We will work on this on Wednesday. It's the last little bit of the chapter, and then we may start to push forward into the next chapter. So that is it for today. If you have any questions, stay around. Otherwise, log off so I know who does and doesn't have questions. And I will see you Wednesday. Bye, guys. Adrian, I'm gonna put you into a waiting room for a minute. Hope, you there?
Yeah.
Hey, sorry, I just saw your emails. I did not check my emails this weekend.
It's okay. I just did my best on it, and
Okay.
I just want to make sure that I did it right before, turning you down for the extension. So for the thing, that's what I wrote down. I don't know if you can kind of see it. I just kind of put the one with the color that it gave off.
Okay. You're cooking spaghetti in water. You have filled it with NaCl. You notice that when the water boils over, it causes the flame of the gas burner to turn bright orange. How would you explain the appearance? Because it has sodium chloride in it. The salt has sodium chloride in it.
So I'm talking about like the unknown solutions, like 3 where you write A, B, C, and then the thing.
Yeah, so you just match them.
So like from 2 where you write down the color of the flame from the video. So you just put which one had the yellow, the green, and the red. Okay. That's what I
So,
thought.
yeah,
But
it's literally just matching the colors.
okay, that's what I did. So
Okay.
okay, I just wanted to make sure I did that one right.
Okay, cool. Cool. Sorry about that with the emails. I was like, oh, she emailed me a couple times. Oh no.
You're
So,
fine.
any other questions?
No, I'm good. Thank you.
Oh, all right, Hope. I'll see you on Wednesday.
See ya.
Bye. Adrian, you there?
Sorry, it didn't let me click off. I thought I